Hey guys, today we are going to complete the chapter Current Electricity that we started in the previous lecture. After studying about electric current, potential, potential difference, resistance, Ohm's law and resistivity, in this lecture we will mainly deal with electromotive force, terminal voltage and combination of resistors. So our first topic is electromotive force. EMF, the potential difference between the terminals of the cell when the circuit is open. It is represented by a Greek symbol epsilon, unit is volt, as same that of the potential, and we know that different kinds of cells have different values of EMF. For example, voltaic cell has EMF value 1.08 volt and for Leclanché cell it is 1.5 volt. Now, the main factors on which EMF of a cell depends. First, material of terminals or electrodes, and second, electrolyte used in cell. There is one special note here. EMF does not depend on the following factors. First, shape of electrodes. Second, amount of electrolytes. Third, amount of current drawn. And fourth, distance between electrodes. There is one more definition of EMF, that is, it is also defined as work done per unit positive charge around the complete circuit of the cell. Mathematically, it is expressed as epsilon equals W by Q naught. Here epsilon is EMF, W equals work done, and Q naught is the test charge. Now the next topic, terminal voltage. It is also the potential difference between the terminals of the cell when the circuit is closed. And it is also defined as the work done per unit positive charge around the circuit of the cell, represented by V. SI unit is volt, and mathematically it is V equals W dash by Q naught. Here V is the terminal voltage, W dash is the work done, and Q naught is the test charge. Now there is one special note here. Terminal voltage of a cell is less than its EMF by the amount of energy spent in the flow of unit positive charge. Now voltage drop, work done in carrying a unit charge through the electrolyte is voltage drop. Mathematically it is V equals W by Q naught. Here V is the voltage drop, W is the work done, and Q naught is the test charge. Now we need to establish the relationship between EMF, terminal voltage and voltage drop. Now, by the law of conservation of energy, we know that energy can neither be created nor be destroyed, but it can be transformed. So here, by the law of conservation of energy, W equals W dash plus W, let it be equation 1. On dividing this equation by Q naught, we are getting W by Q naught equals W dash by Q naught plus W by Q naught. Now we know that W by Q naught equals epsilon, W dash by Q naught equals V, and W by Q naught is equal to V, that is voltage drop. Then equation 2 reduces to epsilon equals V plus V, that is the sum of terminal voltage and voltage drop. This is the required relationship between EMF, terminal voltage and voltage drop. Now next topic, internal resistance. It is simply the resistance offered by the electrolyte inside the cell to the flow of current. It is denoted by R. SI unit is ohm, and we know that from Ohm's law we can write V equals IR. Now a cell is represented with its internal resistance in the figure. Now we need to establish the relationship between EMF, terminal voltage and internal resistance. So for this we have considered a cell of EMF epsilon and internal resistance R, which is used to send current in external circuit in an external resistance R connected across the cell as shown in the figure. From the figure we can say that total resistance of circuit equals capital R plus small r, that is the sum of external as well as internal resistance. Now current drawn from the cell equals EMF by total resistance, so I becomes epsilon by R plus R. So from this epsilon equals I into R plus R. Multiplying this we are getting epsilon equals IR plus IR. Then it becomes epsilon equals V plus V. From this we can find the value of voltage drop, that is voltage drop equals EMF minus terminal voltage. So also we know that internal resistance equals V by I. Instead of this V, we can put the value epsilon minus capital V by I. So this becomes epsilon minus V by V by R, because we know I is equal to V by R. Now taking common R, so we are getting epsilon by V minus 1 into R. This is equation 1, and equation 1 is the required relationship between EMF, terminal voltage and internal resistance of the cell. Now factors affecting the internal resistance of a cell. It depends mainly on the four factors. First one, surface area of electrodes, inversely related. Second, distance between electrodes, inversely related. Then temperature of electrolyte, inversely related. And then concentration of electrolyte, that is directly related. Now we'll see the combination of resistors. Resistors can be combined in two different ways. First one is series combination and second is parallel combination. So first we'll see the first one, that is series combination. In this type of combination, the resistors are connected one after the other, and figure here shows such an arrangement. There is some must-know points that you should know about series combination. First, same current passes through each resistor, as current has a single path for its flow. Second, potential difference across the entire socket is equal to the sum of potential difference across the ends, that is V equals V1 plus V2 plus V3 dot dot dot, as many resistors as you connect. So in series arrangement, the equivalent resistance is equal to the sum of individual resistances. For example, if we consider n, we will connect n resistors, then the combination of resistors is given by Rs equals R1 plus R2 plus R3 plus dot 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 till Rn. Okay, next, parallel combination. The resistors are connected in a manner that the flow of current is different for different resistors. Figure shows such an arrangement. There is also some must-know points concerning the parallel combination. First one, as current is inversely related to resistance from Ohm's law, we know that. So the total sum of currents in a parallel circuit is equal to the current drawn from source, that is I equals I1 plus I2 plus I3 plus dot dot dot. Second, potential difference across each resistor is same, that is V equals V1 equals V2 equals V3 dot dot dot. So in parallel arrangement, the equivalent resistance is equal to the sum of reciprocals of individual resistances. Then 1 by Rp is given as 1 by R1 plus 1 by R2 plus 1 by R3, or Rp equals R1, R2, R3, that is the product of resistances by their sum, that is R1 plus R2 plus R3. Now differences and similarity between series and parallel combination. Differences. In series circuit, there is one pathway. In parallel, two or more pathways. Series, current same anywhere in the circuit, and differences, current splits and passes through different pathways. Voltage is shared in ratio to resistance, and in parallel, voltage is equal in each path. Then resistance adds up and draws less current, and battery lasts longer. And in differences, resistance less and current drawn is less and battery life is short. Now if one bulb fuses, circuit is incomplete in series, but in parallel, if one bulb fuses, the other will still go, and brightness of bulb is less in series circuit because resistance is more, and brightness of bulbs is more in parallel combination. And it is given by the relationship P is equal to 1 VI, that is the expression for power, electric power. Now that's it for today's class. I hope you like it. Keep liking and sharing. Thank you.